in this problem, we're going to consider axial loading on a stepped bar. So here's what our bar looks like. You can see that there's a 1-inch diameter for 12 inches, then it steps down to a 1/2-inch diameter for 8 inches. There's 3 loads applied, one at the end, one at the step, and one in the middle of that 1-inch diameter bar. And what we're asked to find is well, two items. One's what's the maximum stress that occurs in this bar, or more specifically, what's the maximum magnitude of stress, because we may have both tension and compression here. We're looking for the maximum magnitude. And we also want to know how much does point D deflect, that is the free end there, how much does that deflect when this loading is applied. We're told that it's made out of aluminum, and we're given the Young's modulus of aluminum to use as 10 million psi. Well, to start out with, we need to find out what the internal forces are to be able to calculate the stresses and the change in length. So for that, we draw free body diagrams. And we'll start out by looking at segment AB, because there's no loading between A and B here. The free body diagram will look the same wherever we make this cut. And so when we make this cut, we want to look at everything either to the left of that cut or everything to the right. Now, if we look at everything to the right of the cut, we don't even have to mess with the reaction force at point A. So we draw everything to the right of that cut, including all the loads that are applied. And of course, if the total structure is in equilibrium, this segment has to be in equilibrium. And this segment is only in equilibrium if there is this tensile force, or at least an axial force, we think it's tensile, P sub AB. Now I've drawn it as though it's pulling away from the cut face, so that would indicate a tension if the sign comes out to be positive here. When we do the sum of the forces, we'll see that the sign does come out to be positive, 500 pounds. So the place where students tend to make a mistake on these problems is not being consistent with the signs, or by not drawing the free body diagram. Again, the free body diagram looks pretty trivial for this problem, but again, it's a place where you can make mistakes. Now, as we said, we took everything to the right of the cut. We could also have taken everything to the left of the cut, but do remember, if you do that, you have to include the external force at A, which in this case is the reaction force. So from statics, we know that there has to be a 500-pound force at A in the negative x direction in order to maintain equilibrium. Well, for this segment to be in equilibrium, there has to be an axial force on the cut face, and we do the sum of the forces and the x on that free body diagram, and once again find that P sub AB is 500 pounds, just like when we looked at the other segment. So it doesn't matter which segment you look at, everything to the left or everything to the right of your cut, your answer of course will be the same. Now, the directions of the arrows will be different because of the fact that in internal forces, a force that's pulling away from the cut face is tension, or positive, and a force that's acting toward the cut face is negative, or compression. Let's move over to segment BC. We'll make a free body diagram by cutting everything, by cutting through BC and keeping everything to the right of the cut face. And so there are 2 forces that are acting on that section. And again, for equilibrium, we have to have the internal force P sub BC. And by doing the sum of the forces in the x direction, we this time find out that the force is negative 1,500 pounds. And so again, easy place to make mistakes is with signs. So always draw on the free body diagram the force as though it were in tension, and let the signs take care of themselves. If the sign comes out to be positive, it's tension. If it comes out to be negative, it's compression. And so in this case, BC is under compression. Our last segment, segment CD, do a free body diagram by taking everything to the right of the cut, includes the 1,500-pound force on the end, and we'll see that our internal force, P sub CD, has to be 1,500 pounds. So that segment is in tension. So what we found were the 2 segments on the ends are in tension, the segment in the middle is in compression. Can't emphasize enough that this is the main part of this problem, is to get these axial forces correct and to get their signs correct. Now we can just work through segment by segment. To find the stress, we simply divide by the cross-sectional area. So in the case of AB, where we have a 1-inch diameter, there's the area, and so P over A gives us the stress, which turns out to be 637 psi, a tension stress. To find the change in length, we use the equation that the change in length is PL over AE, and we put those numbers in. You can see that L we put in here is 6 inches. That's the length of the segment AB, because the piece of AB, again, that 500-pound force is only applies between A and B. So that's the length that we use there. So that segment of the bar is going to deflect by 3/10,000ths of an inch. Moving to the middle segment, we know it's under compression, so we have the same area as for AB because it's still a 1-inch diameter, and we carry that negative sign through the calculation of both the stress, which comes out to be negative 1910, so that's a compressive stress, and also the change in length calculation comes out to negative. So again, a positive change in length means that it is lengthening, and a negative change in length means that it's contracting, in this case by a little over 1/1000th of an inch. Finally, the last segment is under a tensile force of 1,500 pounds, much smaller area because it's half the diameter. And so your stress comes out to be 7,340 psi, which is the maximum that we've seen. And the change in length comes out to about 6/1000ths of an inch, so much greater than the change in length of the other two segments, because of both the magnitude of the load and the fact that the area is much smaller. So we wanted to know, though, how much, what the deflection of point B was. In other words, how much does the entire bar change in length? So for that, we simply add together the change in length of each of the segments. 2 of them positive, 1 of them negative, and so the total change in length is about 5/1000ths of an inch. And you can see that the when you look at the 3 individually, that the segment CD is the one that stretches the most and is responsible for most of that change in length. So our answer, first of all, the maximum stress was tensile, so the maximum magnitude of stress, 7,340 psi, occurs in that smaller diameter segment CD. And how does point D displace? Because the total bar stretches by this amount, the deflection of point D is going to be 5/1000ths of an inch, a little more than that, to the right.